Guys, how's it going? This is Austin Dennis back with another TryHackMe walkthrough. Today we're going to be going through the intro to LAN room, which stands for local area network. So for task number 1, local area network topologies. So over the years there has been experimentation and implementation of various network designs. In reference to networking, when we refer to the term topology, we are actually referring to the design or look of the network at hand. Let's discuss the advantages and disadvantages of these topologies below. So the star topology. The main premise of a star topology is that the devices are individually connected via a central networking device such as a switch or hub. This topology is the most commonly found today because of its reliability and scalability despite the cost. Any information sent to a device in this topology is sent via the central device to which it connects. Let's explore some of these advantages and disadvantages of this topology below. Because of more cabling and the purchase of dedicated networking equipment is required for this topology, it is more expensive than any of the other topologies. However, despite the added cost, this does provide some significant advantages. For example, this topology is much more scalable in nature, which means that it is very easy to add more devices as the demand for network increases. Unfortunately, the more the network scales, the more maintenance is required to keep the network functional. This increased dependence on maintenance can also make troubleshooting faults much harder. Furthermore, the star topology is still prone to failure, albeit reduced. For example, if the centralized hardware that connects devices fails, these devices will no longer be able to send or receive data. Thankfully, these central hardware devices are often robust. The bus topology. This type of connection relies on a single connection, which is known as a backbone cable. This type of topology is similar to the leaf off of a tree in the sense that all devices' leaves stem from where the branches are on this cable. Because all data destined for each device travels along the same cable, it is very quickly prone to becoming slow and bottlenecked if devices within the topology are simultaneously requesting data. This bottleneck also results in a very difficult troubleshooting because it quickly becomes difficult to identify which device is experiencing issues with data all traveling all along the same route. However, with this said, bus topologies are one of the easier and more cost-efficient topologies to set up because of their expenses, such as cabling or dedicated networking equipment used to connect these devices. Lastly, another disadvantage of the bus topology is that there is little redundancy in place in case of failures. This disadvantage is that there is a single point of failure along the backbone cable. If this cable were to break, devices can no longer receive or transmit data along the bus. And we have the ring topology. The ring topology, also known as a token topology, boasts some similarities. Devices such as computers are connected directly to each other to form a loop, meaning that there is little cabling required and less dependence on dedicated hardware such as within a star topology. A ring topology works by sending data across the loop until it reaches the destined device, using other devices along the loop to forward the data. Interestingly, a device will only send or receive data from another device in this topology if it does not have to send itself. If the device happens to have data to send, it will send its own data first before sending data from another device. Because there's only one direction for data to travel across this topology, it's fairly easy to troubleshoot any faults that arise. However, this is a double-edged sword because it isn't an efficient way of data traveling across a network, as it may have to visit multiple devices first before reaching the intended device. Lastly, ring topologies are less prone to bottlenecks, such as within a bus topology, as large amounts of traffic are not traveling across the network at any one time. The design of this topology does, however, mean that a fault such as a cut cable or broken device will result in the entire network breaking. What is a switch? So switches are dedicated devices within a network that are designed to aggregate multiple other devices such as computers, printers, or any other networking capable device using Ethernet. These various devices plug into a switch's port. Switches are usually found in larger networks such as businesses, schools, or similar sized networks where there are many devices to connect to the network. Switches can connect a large number of devices having ports of 4, 8, 16, 24, 32, and 64 for devices to plug into. Switches are much more efficient than their lesser counterpart, hubs and repeaters. Switches keep track of which device is connected to which port. This way, when they each receive a packet, instead of repeating that packet to every port like a hub would do, it just sends to the intended target, thus reducing network traffic. Both switches and routers can be connected to one another. The ability to do this increases the redundancy, the reliability of a network by adding multiple paths for data to take. If one path goes down, another can be used. Whilst this may reduce the overall performance of a network because packets have to take longer to travel, there is no downtime, a small price to pay considering the alternative. And what is a router? It is a router's job to connect networks and pass data between them. It does this by using routing, hence the name router. Routing is the label given to the process of data traveling across networks. Routing involves creating a path between networks so that this data can be successfully delivered. Routing is useful when devices are connected by many paths, such as in the example diagram below, which is talking about computer A to computer B. In order for these devices to communicate to each other, it would need to send a signal here, jump up here, jump down there, or jump over there, or it could decide to go down here, whichever it has a functionality set to. So attached to this task is an interactive, practical featuring the LAN topologies. Learn about the various ways in which they are vulnerable to breaking. Break the LAN topologies to receive the flag. So first, let's answer a couple of these questions. So what does LAN stand for? And I said that at the beginning if you missed it, but it's local area network. What is the verb given to the job that routers perform? So this is just like the word router. It is routing that they do. What device is used to centrally connect multiple devices on the local network and transmit data to the correct location? Now this is talking about a switch. A switch is the thing that we saw in the very first topology with the star. It's very easy because all the devices just connect straight into that, and then they're able to move around like that. So what topology is cost efficient to set up? So the most cost efficient to set up would be the bus topology. What topology is expensive to set up and maintain? That is going to be the star topology, even though this is the most common one, but the reason that it's so common is because of how well it performs. So now we're supposed to complete the interactive lab that's attached to the task. So right over here, we've got this little site. So in the ring topology, all devices are a connector or to others to create a full circle. Packets of data travel from one device to the next until they have reached their destination. One of the major flaws with the ring topology is that if a device goes down or a cable is broken, then data will no longer be passed. If you hover over the middle of the network cable, you can cut it and see what happens to the packet. So here we've got scissors, we just cut something, and now they can no longer travel on there because the chain has been broken. No other devices can talk to each other. With a bus topology, all devices are connected to a single cable, often called the backbone. Data is sent in both left and right directions down the backbone until the packet's destination is reached. A major flaw in a bus topology is that it can't handle a large amount of data. On the next step, send as many packets quickly as you can try to take down the network. So if we just spam this very quickly, it gets clogged up and there's too many congestions. So that's the biggest issue with the bus topology, is that everything gets just completely overtaken. It can only handle so much, so you're gonna have very slow speeds, lots of data collisions. Why you would not want to do that. So with the star topology, all devices are connected with their own cable to a central switch or hub. Every packet is sent through the switch, which means that if the switch goes down, the network will no longer work. See if you can somehow break the switch. So the only solution here is just to use a hammer and bust it open. But really quick, before we move on and get the flag, just looking at this, the reason that this is so efficient, because with all the other ones, they're all basically just connected using one cable. With this, the only way to break it is to just something to go wrong with the switch, physically break it. But the thing is, if one of these cables gets connected, none of these other devices are affected by that at all. So say that this computer, the cable connecting it to the switch would get broken, none of the other devices on the entire network would be affected other than this computer specifically. That's why it's so common, because once you set it up, the only thing you really have to worry about is the hardware that's actually connecting all of the devices together. But we have now found all of the topology flaws, and we can go ahead and get our flag here, paste it back on the other side, and we have discovered all of the topology flaws. So the next one, a primer on subnetting. So as we've previously discussed throughout the module so far, networks can be found in all shapes and sizes ranging from small to large. Subnetting is the term given to splitting up a network into smaller, miniature networks within itself. Think of it as slicing up a cake for your friends. There's only a certain amount of cake to go around, but everybody wants a piece. Subnetting is you deciding who gets what slice and reserving such a slice in this metaphorical cake. Take a business, for example. You will have different departments such as accounting, finance, human resources. Whilst you know where to send information in real life to the correct department, networks need to know as well. Network administrators use subnetting to categorize and assign specific parts of a network to reflect this. Subnetting is achieved by splitting up the number of hosts that can fit within the network, represented by a number called a subnet mask. Let's refer back to our diagram from the first room in this module. So here we've got the IP address again. If you're not familiar with it, we've got 4 different octets. This is an IPv4 address, and we can have a number anywhere between 0 to 255 in each one of these categories. So as we can recall, an IP address is made up of 4 sections called octets. Same goes for a subnet mask, which is also represented as a number 4 bytes, 32 bits, ranging from 0 to 255. Subnets use IP addresses in 3 different ways. They identify the network address, they identify the host address, they identify the default gateway. Let's split these 3 up to understand their purposes in the table below. So first we've got a network address. The purpose of this is to identify the start of the actual network, and it's used to identify a network's existence. For example, a device with the IP address of 192.168.1.100 will be on the network identified as 192.168.1.0. So the host address, an IP address here, is used to identify the device that's on the subnetwork. So for example, a device will have the network address of 192.168.1.1. And an example of this would be 192.168.1.100, which is the device that we've referenced up here. So basically, this 0 is all of your host bits. So anything between 0 to 200, anything between 1 and 254 on this specific subnetwork could be a host. Now the back would be the default gateway. So the default gateway address is a special address assigned to a device on the network that is capable of sending information to another network. Any data that needs to go to the device that isn't on the same network, for example, 192.168.1.0, that's the network that we're talking about, will be sent to this device. These devices can use any host address, but usually either the first or last host in a network, which is .1 or .254. Now, in small networks such as at home, you'll be on one subnet, as there's unlikely a chance that you need more than 254 devices connected at one time. However, places such as businesses and offices will have much more of these devices, PCs, printers, cameras, and sensors, where subnetting takes place. Subnetting provides a range of benefits, including efficiency, security, and full control. We'll come on to explore how subnetting provides these benefits at a later date. However, for now, all we need to understand is the security element to it. Let's take a typical cafe on the street. The cafe will have 2 networks, one for employees, cash registers, and other devices in the facility, one for the general public to use as a hotspot. Subnetting allows you to separate these 2 cases from each other whilst having the full benefits of connecting larger networks such as the internet. So right here, you've got an example of subnetting for one entire company that's accounting for accounting, human resources, and finance. The reason that you need to understand subnetting and cybersecurity, say that you're setting up a network for some reason and you've got a bunch of different departments in the thing, you can't have every person in the department be able to access every little thing. So for example, you're not really going to want your human resources to be able to directly access all the finance. You know, say that you have an online store that stores credit card information so that people can come back and just easily purchase their things without having to enter in their full credit card information. You don't want to have human resource be able to access that piece of the website. You don't really want anybody other than someone that absolutely needs to access that information having access to it. And you wouldn't want to just bring somebody in and on the first day of work they have the same exact access to a network that the CEO or the network administrator does. That's why we use subnetting. That's why later on you'll learn about putting people into groups and limiting their access to things. That's the whole reason that subnetting is a thing. So what is the technical term for dividing a network into smaller pieces? So this would be referring to subnetting. How many bits are in a subnet mask? So this is the same thing as an IP address, that's 32 bits. What is the range of a section of a subnet mask? So this is asking about what the bits are, what it can be from, and that is 0 to 255. What address is used to identify the start of a network? This is a network address. What address is used to identify devices within a network? This would be a host address. So you have to have a network address, you have to have a default gateway, which is what the next question is going to be asking about. And everything in between those two addresses, actually not everything in between, you also have a broadcast address that you've got. But everything in between the network address and the broadcast address, which is the very last in the network, you are able to use as a host address. So what is the name used to identify the device responsible for sending data to another network? That would be your default gateway. All right, now we're going to look at the address resolution protocol, or the ARP protocol. So recalling from our previous tasks that devices can have two identifiers, a MAC address and an IP address. The address resolution protocol, for short, is the technology that is responsible for allowing devices to identify themselves on a network. Simply, the ARP protocol allows a device to associate its MAC address with the IP address on the network. Each device on a network will keep a log of the MAC addresses associated with other devices. When devices wish to communicate with each other, they will send a broadcast to the entire network searching for a specific device. Devices can use the ARP protocol to find the MAC address and therefore the physical identifier of a device for communication. How does address resolution protocol work? Each device within a network has a ledger to store information on, which is called a cache. In the context of ARP protocol, this cache stores the identifiers of the other devices on the network. In order to map these two identifiers together, IP address and MAC address, the ARP protocol sends two types of messages, an ARP request and an ARP reply. When an ARP request is sent, a message is broadcast to every other device found on a network by the device, asking whether or not the device's MAC address matches the requested IP address. If the device does have the requested IP address, an ARP reply is returned to the initial device to acknowledge this. The initial device will now remember this and store it within its cache, an ARP entry. This process is illustrated in the diagram below. So right here we've got a device sending out a ARP request, and they're sending out to every single one of these devices asking who has the address of 192.168.1.10. And as it sends it out to all these different ones, this device right here sends a ARP reply back saying that they have the IP address of 192.168.1.10. So what does ARP stand for? I mentioned it earlier, address resolution, oops, spelled that wrong, resolution protocol. What category of an ARP packet asks a device whether or not it has a specific IP address? That would be a request. What address is used as a physical identifier for a device on the network? That would be your MAC address. I didn't even spell address right, but it still gave us the right answer. It says what address is used as a logical identifier for a device on a network. That would be the IP address. So now we're going to take a look at the DHCP protocol. IP addresses can be assigned either manually by entering them physically into a device or automatically and most commonly using a DHCP, Dynamic Host Configuration Protocol server. When a device connects to a network and if it has not already been manually assigned with an IP address, it sends out a request, DHCP discover, to see if any DHCP servers are on the network. The DHCP server then replies back with an IP address the device could use, DHCP offer. The device then sends a reply confirming it wants the offered IP address, DHCP request. And then lastly, the DHCP server sends a reply acknowledging that this has been completed and the device can start using the IP address DHCP ACK. So here's a diagram of that. So basically, this will send out an IP address that has nothing, just 0.0.0.0. And it will find a DHCP server. They will offer a specific IP address for a host that isn't being used yet. They will confirm that they would be okay using that, and then the DHCP server will give them that address and they'll lease it out for a certain amount of time. And then if the device is still on the network, it needs to do it again. The exact same process will just happen over and over again. But the thing you need to know about a DHCP server is that it's on leases. So you don't just get an IP address permanently from a DHCP server. It's set up for a certain amount of time. And you need to figure out what the good balance would be between, you don't want to set it up for like a year, because then you're eventually going to run out of IP addresses, because you can only do so many IP addresses for a specific network. But at the same time, you don't want it to be for like 5 minutes, because then you're going to overwhelm your DHCP server, because you're just going to constantly have to be rehashing out new IP addresses, and it's just going to get really annoying to deal with. So what type of DHCP packet is used by a device to retrieve an IP address? This is talking about a DHCP discover. What type of DHCP packet does a device send once it has been offered an IP address by the DHCP server? So this is this moment right here. It gets offered it, and then it comes to a request. So DHCP request. Finally, what is the last DHCP packet that is sent from a device from a DHCP server? So this is what gets sent back after you send a DHCP request, and this is a DHCP ACK. So this isn't something that you need to just perfectly remember. All these things happen manually, but as a cybersecurity professional, it's important to understand what's happening behind the scenes, so that when you're looking at network traffic like this, you need to know whether to be alarmed or not alarmed. So that is the end of this room. It talks about us continuing our learning, looking at the OSI model. So in a future video, we will be doing that, but I hope that you enjoyed this video. Hope I was able to make sense of some of these things and explain these network topologies a little bit better if you didn't understand them before. But I hope this video is helpful to you. Like, subscribe, share the video with your friends, help them to see this and grow the channel, so that we can keep on helping people learn more about cybersecurity and ultimately keep everybody's network a lot safer. So thank you so much for watching. Hope you have a great rest of your day.